Hello everybody, we start our 8th lecture. So today is section 8.1, some limits to remember. So we consider here several examples. Example 1. Example 1. Limit as n tends to 1 nth root of a equals to 1, where a greater than 0. Okay, proof. First, we consider the case a is greater than 1. Then, what we have, okay, we write as follows. Then, for sure, nth root of a is greater than 1, and we'll substitute alpha n, by definition is nth root of a minus 1. And then this is a positive number for all natural n. So, then what is the relation between alpha n and our a? We may find easily that a equals to alpha n plus 1 power n. Then we may apply Bernoulli Inequality. So Bernoulli Inequality says this is greater or equal than 1 plus alpha n times n. So let me rewrite this inequality as follows: alpha n less or equal than a minus 1 over n. So, if we consider the last two inequalities together, we obtain 0 less than alpha n less or equal than a minus 1 over n. Now we have two policemen here and there. So as n tends to infinity, as we know, we have both sequences tend to 0. Вы видели, кто-то написал? Не может видеть. Что за? So we deduce by two policeman theorem, that alpha n tends to 0 as well. And that is in fact the same as to say limit as n tends to infinity alpha n is 0 is equivalent to say the limit of nth root of a equals to 1, because you see that is done. Okay, for a equals to 1, nothing to prove, almost nothing to prove, and maybe this is a kind of example. In fact, it was used here as well, right? So we have the sequence as follows: x n equals to 1 for all n. So we have a constant sequence, and it converges to 1. Why? Because by definition, for arbitrary epsilon greater than 0, we can choose capital N natural number such that for all n greater than n, we have xn minus 1 less than epsilon, and we can choose n equals to 1 for arbitrary epsilon greater than 0. Why? Because here xn minus 1 equals to 0, hence it has modular less than epsilon for all positive epsilon. So a equals to 1, it's okay. And the last case, a is between 0 and 1, then what we can consider, we can put b equals to 1 over a, then this number is greater than 1, hence part 1 guarantees limit as n tends to 1 nth root of 1 over a equals to 1. So, okay, this is b, right, under nth root. And it means limit as n tends to 1 by properties of roots 1 over nth root of a equals to 1. And then we have the limit of nth roots of a is equal to 1 as well. So so it's okay. It's done. Okay. Next example. Example 2. Example 2. Example 2. What is example 2? For any real number a, limit as n tends to infinity a power n over n power k is, no, not that one, which, n factorial, yeah, n factorial. N factorial is 0. So how may write members of our sequence in modulus? So modulo a power n over n factorial. Let's consider modulo of our sequence, members of our sequence. So we may rewrite modulo a times modulo a, so on n times, over 1 times 2 times so on times n. The same number of multipliers in both numerator and denominator. Then, by Archimedean property, the set of natural numbers is not bounded, hence modulo a is not an upper bound, so there exists natural m such that m plus 1 is greater than modulo a. So now I can split our product, and we may consider this fraction as a product of n fractions, into two parts. The first one contains m terms, modulo a times modulo a, so on up to modulo a, and in denominator first m terms, and then other terms as follows. So in fact, up to now I just split the fraction into the product of two fractions, and then we can estimate it, less or equal. In fact, strictly less, but doesn't matter. So the first, let it be as it is. And the second one, we replace every multiplier in the denominator by the smallest one. The smallest is m plus 1. Hence, we have modulo a over m plus 1. So every term in our product is replaced by the same term, this one. So how many terms we have here? Altogether we had n terms. We split m terms, and the rest contains n minus m terms. That is the estimate. So now I can use properties of powers, so we may rewrite it as a to the power, okay, let it be, yeah, that is m plus 1 power m over m factorial times modulo a over m plus 1 power n. So we cancel powers m of modulo a, m plus 1 power m is here, and the rest is as it is. Now modulo A over m plus 1 is less than 1, and and then we can use another limit, q to the power n equals to 0, if modulo q is less than 1. Using this example, we can estimate as follows. So the right hand side tends to 0 as n tends to infinity. Why? Because m is fixed. Once we have modulo A, we can choose such a natural m, we fix it. Of course, we should take here n is greater than, so here I should suppose n is greater than m. Otherwise, we cannot split like that. But when n tends to infinity, we can always suppose it. And so here we have a product of a sequence which has 0 as a limit and a constant term. So the product gives 0 in the limit. The left hand side tends to 0 as well. So the middle tends to 0 by two-policeman theorem. And that is the end of the proof. Okay. Yeah. Then, next example uses the binomial theorem. Example 3. Example 3. If a greater than 1, then limit as n tends to infinity, n to the power k over a to the power n equals to 0 for all k. In fact, natural. Yeah, in fact, here we may put also reals, but we don't know real powers yet. We can put also rationals or integers, no problem, but in fact, you will see it's sufficient to prove just for one proof. So firstly consider the case k equals to 1. Then we may estimate as follows. So we need to consider this fraction. Of course, this is something positive. But now we may write it as follows: 1 plus a minus 1 power n. Then binomial theorem says that is sum k, okay, k is not good, j from 0 to n, binomial coefficient nj times 1 power j, a minus 1 power n minus j. Then I can choose, a is greater than 1, so a minus 1 is positive. Hence we have the sum of n plus 1 positive terms in the denominator, n plus 1 positive terms, and I'll forget about all terms except a particular one. Which one? Okay, let me choose it. Let's say, let's consider j equals to n minus 2, that one, this particular term. So n over n minus 2, 1 power n minus 2, a minus 1 power n minus 2. What is it? What is it? N over n factorial, 2 factorial, n minus 2 factorial, 2 factorial, a minus 1 power squared. And that is, what is n factorial over n minus 2 factorial? We divide product of the first n natural numbers by the product of the first n minus 2 natural numbers. So two numbers remain not cancelled after cancelling common multipliers in both factorials. So we have n times n minus 1 only, cancel with n, and we have 2 over n minus 1, a minus 1 squared. And as n goes to infinity, this tends to 0. And same is for the left-hand side. So, two-policeman theorem again says that the limit of n over a to the power n equals to 1. 0. Equals to 0. Okay, so it means the case k equals to 1 is ready. Then what we can do, we can put in general case. So we make a in general case, we may rewrite it as n over kth root of a power k. Sorry, here power n, I forget. So it means we represent a to the power n as a to the power n over k times k. And a to the power n over k is precisely that one. Kth root of a to the power n. So, then you see the number in brackets tends to 0 since we have proved it. Kth root of A is positive, is greater than 1, greater than 1. And then we have power k. K is a natural number, so we have k terms, and it gives the product of k zeros, so the example is proved. Okay, one more example. Similar to that one. Just proved, better to say similar. It doesn't look similar, but it is proved similarly. So example 4. The limit as n tends to infinity, nth root of n equals to 1. That is, by the way, is a very useful example which shows rather strange thing from the first glance. So look, we have n to the power 1 over n. N tends to infinity, the power tends to 0. So we have something like that. That is indeterminacy. Infinity power 0. So infinity power 0 may have a limit 1. Okay, let's prove it. First of all, by the property of nth root, clear nth root of n greater than 1. Because n is greater than 1 for n greater than 1, right? Hence, if we denote alpha n equals to nth root of n minus 1, that is a positive number for n greater than 1. And we may remark that n equals to alpha n plus 1 power n, like in the first example today. And then let's apply, firstly, let's apply the binomial theorem. So I'll write it here. And j and then alpha n power j 1 power n minus j. Alpha n is positive, hence we have positive terms, we have n plus 1 positive terms in our sum. So the sum is greater than just one term, and here I'll choose the term with j equals to 2. So n2 alpha n squared, and that is n2 was computed like n minus 2, so and that is n times n minus 1 over 2 alpha n squared. So we obtained the inequality a n squared less than 2 over n minus 1. So cancel n, and we have this one. Of course, this is a positive number. Again, by two policeman theorem, both sequences tend to 0, hence alpha n squared tends to 0 as well. So we have proved limit as n tends to infinity alpha n squared equals to 0. It means, by definition, for arbitrary epsilon greater than 0, we can find, better to say, natural n such that for all n greater than this natural n, we have alpha n squared less than epsilon. I can forget about modulus because of square. But then the last inequality, and maybe it's better to proceed like follows. Look, here we have something for arbitrary epsilon. Let me put it epsilon prime. And then for arbitrary epsilon greater than 0, I'll put epsilon prime equals to epsilon squared. So take arbitrary epsilon greater than 0, then put epsilon prime equals to epsilon squared, which is also greater than 0. For this epsilon prime, we can choose capital N. So we find capital N such that for all n greater than n, we have alpha n squared less than epsilon squared. The last inequality is equivalent to modulo alpha n less than epsilon. Remember, alpha n is positive, so we may forget about modulus. Or maybe it doesn't matter, right? Yeah, so in fact, that is what we wanted to prove. So it means the limit as n tends to infinity alpha n equals to 0. That. Okay, let me put modulo here, because in the definition we should put modulo, although that is positive, so don't need. Fourth example. Yeah, but this question, how did we get the two policemen? 2 over n minus 1. Yeah. Yeah, 2 over n minus 1, it's okay. Yeah, but look to the inequality. N greater than alpha n squared times n minus 1 over 2. Cancel n, and 2 over n minus 1 is here. Is it? Maybe the question why it tends to 0. Okay, I may rewrite, if it is not clear like that, 2 over n times 1 minus 1 over n. That is, let me write like that, 2 times 1 over n times 1 over 1 minus 1 over n. And then by properties of the limit. Yeah? Look. This one, so tends to 0, hence this tends to 1. 1 times 0 times 2, we have 0. And this inequality, once again, follows by n greater this. Is it okay? Okay. So, yeah. Now we finished our example, and in fact we have finished the section 8.1 because these are rather important examples, and especially this one is not obvious, but also that one, you see what it says, that an exponential tends forces such a ratio to go to 0. So it means that exponential grows essentially faster than powers of. That is also rather important conclusion, which is used very, very often. Okay. Now we'll consider monotonic sequences. So section 8.2. Monotonic sequences. Monotone sequences. Monotonicity. Monotone sequences. Definition. Xn sequence is increasing if for all n natural xn less or equal than xn plus 1. And also we will say strictly increasing if the inequality is strict. And analogously, xn n equals to 1 up to infinity is decreasing if for all n natural xn greater or equal than n xn plus 1. So strictly increasing or decreasing. That is some kind of terms as well. Okay, let's have a break. Okay, let's continue. So, what do we have? We have defined increasing, strictly increasing, decreasing, strictly decreasing sequences. Now let me give an example. Example 1. Xn equals to 1 over n. So here we have n is strictly less than n plus 1, hence 1 over n is greater than 1 over n plus 1 by one of axioms. And that is xn greater than xn plus 1, so it means xn is strictly decreasing. Example 2. Xn equals to n plus 1 over 2 n minus 1. We need to prove this is decreasing sequence. So x1 is 2 over 1, 2. x2 is 3 over 3 is 1 less than x1, and we want to check if xn is greater than xn plus 1. So there are many ways to do it. So for example, just to compare xn and xn plus 1, that is, what is the sign between them, right? So we want to prove this is greater, so we don't know the sign yet. We compare, we don't know if it's true or not, but those two lines are equivalent. So if I'll substitute here n plus 1 instead of n, we have n plus 2 over 2n plus 1, and that is equivalent to, by properties, n plus 1 times 2n plus 1, n plus 2 times 2n minus 1. That is again equivalent to 2n squared plus 2n plus 3n plus 1, 2n squared 4n plus 3n minus 2. And you see that indeed we have the correct inequality 1 greater than minus 2. And since all inequalities were equivalent to each other, before we didn't know about precise sign of inequality, but in the very And at the very end, we got the inequality greater. So it's done. Hence, that is indeed is strictly decreasing. Why that is important? Because of the following result. That is theorem 1, Weierstrass, monotonicity, monotone. Okay, just the alpha is Weierstrass, and if xn is monotone, oh, I forget to say what means monotone, monotone and bounded, then it converges. So monotone is any of those definitions. So monotone, those are monotone. Okay, proof of the theorem 1. So let us choose something for definiteness. So monotone means either increasing or decreasing. So suppose xn is increasing. It is bounded above. Hence, the set A, if we put A, x1, x2, so on, that is slightly different from this notation. Why? Because in a sequence it may happen that one term is repeating several times, but of course here for the set it doesn't matter. We don't repeat one element of the set several times, it doesn't matter. So these are just real numbers which are among the members of our sequence. So this set is bounded above, and non-empty. Why it's non-empty? Because at least one element we have, x1 at least, right? It may happen that we have x1, x1, and so on. Constant sequence also is increasing according to the definition. So there exists the least upper bound, supremum. Let it be, okay, L. Which is a real number, right? real number. By the definition of the least upper bound, what means least upper bound? It means that for arbitrary epsilon greater than 0, L minus epsilon is not an upper bound, hence there exists an element of A, let's say A in A, such that L minus epsilon less A less or equal our L. That is according to the definition of the supremum. So this is the least upper bound. Now, what is A is in A? A small in A capital. A capital consists of members of our sequence. So it means there exists a natural such that xn equals to A. And it means that what we have found for arbitrary epsilon greater than 0, there exists n natural such that L minus epsilon less xn less or equal L. Now, what happens for arbitrary and small greater than capital N? Look, we may write the following chain of inequalities: xn less or equal xn plus 1 less or equal xn plus 2, and so on, less or equal than sooner or later we'll meet our xn small, because n is greater than capital N. And then, for sure, xn is less or equal than L, since L is the upper bound for the set capital A, so for all members of our sequence. So, altogether, what we deduce for arbitrary epsilon, we have found capital N, such that for all n greater than capital N, we have L minus epsilon less than x n small less or equal L, which is definitely less than L plus epsilon. The last inequality is equivalent to xn minus L less than epsilon. The last, this double inequality. That's the end of the proof. And let me make a remark. So if xn is increasing and bounded above, then the limit exists and is equal to supremum of all of the set of an. Maybe I write like that, where n contains all naturals. And analogously, if xn is decreasing and bounded below, then the limit exists and is equal to the infimum of the same set of all members of our sequence. So for supremum we have proved, for infimum this is either analogously or just to take minuses. Okay, that is about Weierstrass theorem. Now some example how it works, and it works very good for recurrence relations. So example, an is defined as follows. So a1 is 2, an plus 1 equals to an plus 5 over 3 for n greater or equal 1. So the sequence is convergent and find the limit. Solution. So first of all, look at A2. A2 is, if we substitute n equals to 1, then we have a1 plus 5 over 3. a1 is 2, so we have 7 over 3. 7 over 3 is greater than 2. So it gives some kind of supposition that in fact an is increasing. Okay, how we can check it? Look, so proof an less than an plus 1 for all natural n. By induction, we proceed by induction. By induction, choose firstly the first step, n equals to 1. We checked. a1 is 2 less than 7 over 3. What is a2? We have checked it. So, induction hypothesis, for n equals to k, we have ak less than ak plus 1. So, we need to check if it's true for n equals to k plus 1. ak plus 1, if it is indeed, if it is true, it is indeed less than ak plus 2. Okay, we need to compare those two. And then how we can proceed. This inequality is equivalent to, okay, what is ak plus 1? It's ak plus 5 over 3. So this is equivalent to check that one. That is again equivalent to, we may multiply both parts by 3. It's equivalent, ak plus 5 less than ak plus 1 plus 5. And that is valid inequality, true inequality, right? So, other way is to start from the induction hypothesis. So we suppose it's true, and then if it is true, we add the same number 5 to both sides. That's true as well. Then divide both sides by 3. We have that inequality, and that is precisely what we want. That is, it means that indeed the sequence is increasing. If it is increasing, then it is for sure bounded below, because every term is greater than a1. a1 is 2, right? So for sure, all members of our sequence, but say the sequence is bounded below. Now how to prove it's bounded above? So, we should somehow suppose an upper bound, and then to check that it is indeed an upper bound. So, what is upper bound? Look, the first number less than 5, when you add two numbers, one of them is less than 5, and then divide by 3. 3 is greater than 2. Half of the sum is for sure less than 5, and this is smaller than 5, right? So let us prove a n less than 5 for all natural n. And again, we do it by induction. So the first step, n equals to 1. a1, what is 2, is smaller than 5. Okay, true. Now, the induction hypothesis says that ak less than 5 for certain index k. Then we should check n equals to k plus 1 if it is valid for n equals to k plus 1. Okay? Look, ak plus 1 is ak plus 5 over 3, smaller than, since ak is smaller than 5, 5 plus 5 over 3, that is 10 over 3, that is smaller than 5. So it is proved. Hence, we have proved that the sequence n is monotone, in fact increasing, strictly increasing, and bounded. So it means, according to the Weierstrass theorem, there exists the limit. The sequence, in fact, it is equal to the supremum, but it is not so important at the moment. So by Weierstrass theorem. So, look, what we need now. We checked the first part of our example, namely, we have done this. Show the sequence is convergent. It's okay. Now we need to find the limit. Look at the equality at our recurrence equality. Now we know that an tends to something. So put the limit an equals to a. Then the limit of an plus 1 is also a. So what we can do now? Look at this equality. We know both limits exist. Hence, what we have, if we take the limit in both sides, we have a equals to a plus 5 over 3. That is 3a equals to a plus 5, or 2a equals to 5, or a equals to 5 over 2. And that is the answer. That is the answer. Let me take a caution, make a caution. Be careful. Because this looks very nice. Just take a limit and that's all. But let's consider the sequence minus n power n. You can also write a recurrence relation. xn plus 1 equals to minus xn. Then, look, if we repeat the last part, limit, denote limit of xn equals to a, then the limit of xn plus 1 is also a, and what we have from this? A equals to minus a, hence a equals to 0. That is not true. We know the sequence xn is divergent. So that is not true. We cannot start with this notation. No right to do it. Because here, first we have proved the existence of a limit by Weierstrass theorem. Only after that we used the consideration with this taking the limit. One more example. example 2. Show the sequence I forget to put that. Show that the sequence is convergent. That the sequence xn equals to sum k from 1 up to n 1 over k plus 1 is bounded and monotonically increasing. I'll modify it slightly. K squared is convergent. That is more interesting. It's convergent. So, first of all, solution. We observe that xn plus 1 minus xn is equal to the very last term which is added to the sum. So xn is the sum of the first terms 1 over k squared, and then we add one more term, this one, and that is positive. So xn is strictly increasing. Now we need to prove it is bounded. That is not so easy. So k is smaller than k plus 1, hence 1 over k is, okay, maybe I'll choose, k is greater than k minus 1, hence 1 over k is smaller than 1 over k minus 1. K is greater than 1. Then, how we can proceed? Xn equals to 1 plus 1 over 2 squared plus 1 over 3 squared plus so on plus 1 over n squared. That is, now we can estimate it like that. Less or equal 1 plus 1 over 2 times 1 plus 1 over 3 times 2 plus so on plus 1 over n times n minus 1. That is, if we'll use that one. Now, the nice observation is the following. Look, 1 plus 1 minus 1/2 plus 1/3, 1 over 2 minus 1/3 plus so on plus 1 over n minus 1 minus 1 over n. So, in general, 1 over k times k minus 1 equals to 1 over k minus 1 minus 1 over k. Because if you find the difference, you have k minus 1 over k times k minus 1. That is indeed 1 over k times k minus 1. monotonicity. This one, I guess. The question is about monotonicity here. Once again, xn is the sum of, like that. That is xn, right? Xn plus 1, you have one term more. And this one term is precisely that one. That one. So xn plus 1 minus xn is that last term of the sum. I hope it's okay. Yeah? Okay. Now look, this is so-called telescopic sum. So 1 plus 1, it's okay here. Then look what happens. 1/2 is cancelled. 1/3 will be cancelled with the next one. And in fact, 1 over n minus 1 will be cancelled with the former term. So 2 minus 1 over n. And that is smaller than 2.